Hello, everyone. So I have I had a good question about number 18, and I went back and looked at 18, and I didn't like it the way it had been written, so I changed it up. Instead of electron, it's going to be a neutron that you'll see there, and hopefully some of you have already attempted it or gotten there, and unfortunately I'm sorry, I've changed the mass of the particle. It's no longer an electron, it'll be a neutrino. And then of course problem 12, just a little note. So what are we doing here? We've got physics 1105, homework number 1, and I'm just going to write down what we know. Number 12 has been changed. So that's really all you need to know about that. So 12, it's not hard, you do it again. If you've already done it once, I don't know how you did it because it really didn't make sense. So anyway, number 12, you probably weren't able to do in the first place. All right. But we're not here to talk about number 12. We're here to talk about number 18. 18. Okay, so here's 18. We've got, all right, so let me draw this super awesome picture. Here's a spiral galaxy. Let's call it Andromeda. And, you know, they call it a spiral galaxy, but it's just constituted of a lot of stars that have formed spiral waves inside of them, made of stars. How about that? We're going to erase here. Come on. There we go. So let's say this is Andromeda. Okay, you guys don't know probably a lot about galaxies and whatnot, but Andromeda is our closest galaxy system, large galaxy. And it's about the same size as we are, the Milky Way galaxy. And actually, that Andromeda galaxy and the Milky Way galaxy are moving toward each other, interestingly. And in a few billion years, they'll mix. Okay, so I'm not going to draw our galaxy, but we're over here, and let's say this is the Earth, and I can't even draw the sun because it would be too far away. So here's our Earth, okay? Somewhere in Andromeda, doesn't matter where, I'm going to pick a point, there was a supernova at that point. A supernova is when a star explodes. It's too heavy to hold itself up anymore after it starts producing iron on its interior. It can't hold itself up anymore, and then it kind of it just goes ballistic. It just does a thing where they've been known to be brighter than entire galaxies. The supernova itself, it just is an immense amount of energy that pops out, and all kinds of stuff come out of it. So everything, all kinds of things radiate from this supernova, and we're going to pretend that it came out of the Andromeda galaxy. Well, one of those particles, this guy right here, is heading straight for Earth. Okay? And it's a neutrino. That's the symbol nu. Greek letter nu, and that neutrino is moving toward us. And it's coming our way, so let's get ready for it. And I changed the equation, I changed the speed at which it's going. I changed it to 8.5, so its velocity of the neutrino is going 8.5 times 10 to the 3 meters per second. Okay, well that's really slow. I'm doing this on purpose. I don't know if that's a physical reality, actually, that they would even go that slow. But I'm doing it this way anyway, just so that we can get a good number in the end. Okay, so what is it that we're actually doing? We are applying, let's write down the mass of the neutrino. First, the mass, 1.25 times 10 to the minus 37 kilograms. Okay. So we have its momentum, which is your mass times velocity. And we can say that the momentum P is equal to 8.5 times 10 to the 3 times 1.25 times 10 to the minus 37. And of course that is in kilogram meters per second. So our momentum P is, let me get my calculator. Okay, here we go. 8.5 times 1.25. That's 10.625. 10.625. And now I've got 10 to the 3 times 10 to the 37, so that's going to be 10 to the minus 34 times 10 to the minus 34. And if we want to do this in terms of significant notation, we're going to say that our momentum is 1.06, because we can just drop those guys. They're nothing after we get down that small. And times 10, so we divided by 10 here. When we move the decimal point over, we divide by 10. So we have to multiply by 10 on the 10 to the 34, but it's 10 to the minus 34. So 10 to the minus 34 multiplied by 10 is 10 to the minus 33. And that is in kilogram meters per second. So kilogram meters per second. So we've got our guy, and we know its momentum. That's its momentum. Momentum is a vector. So for anyone who's watching this video, I hope you're watching, because I hope everybody's watching, but this is the price you pay for not watching. I'm going to make a note right now. The quiz is going to have a question on what is momentum, and that question is going to be on the quiz. So is momentum mass times velocity? Yes. So quiz. Momentum equals mass times velocity. All right. So that's your reward for watching this video. I've already written it right here. Momentum equals mass times velocity. All right, so we've got our momentum there. All right, and it's coming straight for the Earth. It's heading straight for us. Here we are on Earth. Don't be afraid. Neutrinos pass through us all the time. Billions of them. Okay, so we have the momentum of the neutrino. Let's put a little neutrino on there so we know what that is. Okay. Now, hopefully, you guys will be watching the second video from Crash Course. They're calling it the quantum mechanics videos. Yes, that's true. It's quantum mechanics. However, it's really not that crazy. The stuff that they're talking about, as far as I'm concerned, it all kind of makes sense, and hopefully it will to you also by the end of this semester, or in a few weeks actually. So let's get to it. The Heisenberg uncertainty principle. Uncertainty principle. So Heisenberg said, because de Broglie, however you want to pronounce it, de Broglie, he did this equation that we've been using to figure out the wavelength of a particle. So we're going to take Planck's constant and divide it by the mass and the velocity of a particle. So really, what is that? That's really Planck's constant divided by the momentum, right, of that particle. And that gives you your wavelength, and you can do it yourself. You can figure out what your momentum is. So you know your mass, right? I'm 100 kilograms, and if I'm going down the road at 30 meters per second times 30 meters per second, then my momentum, P, is equal to kilograms, is equal to 100 times 30. That's 10 to the 3. So 100 times 30, 100 times 10 is 3,000 is what that is. So 3,000 kilogram meters per second. That's just me. Okay, let's box that over. Me going fast. Okay, really fast for a person. I can't run that fast. Okay, so I could figure out what my de Broglie wavelength is, de Broglie, if I were to put this P in below Planck's constant. And we've talked about it before, Planck, Planck's constant is equal to H, and that is 6.6 times 10 to the minus 34 joule seconds. Do I have that right? I want to make sure I got it to the right. Okay. So far, so good. So we know what the momentum, this is the momentum of me. This is the momentum right here of a neutrino. Okay? And what we really want to know is using Heisenberg's uncertainty principle, which says that the unknown distance of x, we don't know, it has a beginning and it has an end, times the unknown region of momentum has to be greater than or equal to Heisenberg's uncertainty principle divided by 4 pi. Planck's constant, this is Planck's constant, divided by 4 pi. Okay. But we know this one exactly. We know it. So we don't have to all of our uncertainty is here. So here we have uncertainty. Here, under the momentum, no uncertainty. Okay, so we can then say that Planck's constant divided by 4 pi is less than or equal to delta x times our p that we know for sure. We don't know this, but we do know that. So what do we want to do? We want to solve for the range that this could be, because we know p. And we know p, it's right here. That's our momentum. Okay? So we're going to do it very quickly. Delta x, the range of x that we can possibly have, has to be greater than or equal to Planck's constant divided by 4 pi times our momentum of the neutrino. And that's as easy as it gets. Can't get any easier than that. So here's the supernova explosion. Here's our neutrino. So over here we've got supernova explosion. We've got a neutrino coming our way. Here's Earth. And that neutrino can be found anywhere between here and here. And that distance is delta x. So that delta x is going to be delta x is greater than or equal to 3, I messed up, that's not 3, it's 6.66. 6.6 times 10 to the minus 34. I'm not going to put units on because in the end, all the units are going to cancel out and we're going to be left with meters. We're going to put a 4 pi here. You guys know that pi is equal to 3.1416. I always go the extra little digit here on the 6. It helps get your, I don't know. You can say 3.14. I'm sure you'll get the right answer. No big whoop. Okay, 3.1416. And we're going to multiply that by 1.06 times 10 to the minus 33, because that is this number. Okay, we've written it up here. So that's this, and we've got basically this is the equation for the answer, and all we have to do now is plug it in. So it can be greater than or equal to, we're going to just say it's equal to, okay? And that'll be it for us. It could be greater than or equal to. If you guys leave a greater than sign in there, that's the proper way to do it. The answer technically then, of course, is still right. It doesn't matter. So 6.6, we're going to enter that in. We're going to divide by 4. We're going to divide by 3.1416. We're going to also divide by 1.06. And then we're going to get 10 to the minus 33 in the bottom. and 10 to the minus 34 on the top leaves us with 10 to the minus 1. So whatever we get here, which is 0.495 times 10 to the minus 1. So that really equals 10 to the minus 1 would move us over once. 4.95 times 10 to the minus 2. Did I do that right? Move that, multiply by 10, divide by 10. Yep, that's right. Okay, and that's in meters. So, what do we have in the end? We have our delta x is greater than or equal to 4.95 times 10 to the minus 2 meters. Or, if you want to think of it, that is 4.95, which is almost 5 centimeters. So the distance, delta x, can be, here, this distance is 5 centimeters. So somehow, some way within 5 centimeters, we would find that neutrino. So even though it's a very, very, very small particle, it could be anywhere in those 5 centimeters. We don't know where it would be. You just don't know. That's the whole notion of the uncertainty principle. Okay? That's the whole notion behind this here Heisenberg uncertainty principle. And so, of course, if you know your position very well, if you know this very well, then this is widely ranging. If you know the position really well, then this is widely ranging. Okay? And Planck's constant is at the root of the whole thing. All right, guys, that's it. I don't think there's anything else, but if you guys have questions, email me, and I'll hopefully get back to you by Monday. And good luck on the quiz.